We're going to take a look at this concept of intervals of convergence. And in this first example, we're just going to apply it to the geometric series. And later on, we're going to apply this concept to any series, whether it's geometric or something else. But it'll be pretty easy to understand and learn it via the geometric series. And as we go through here, some of the vocabulary that you're going to need to know, and it's going to come naturally as we go through here, are these 4 points. So you probably don't even know what an interval of convergence is, although you do know what convergence is. In this case, we have the simplest of geometric series, and I know this is a convergent geometric series because r is less than 1. If I want to be mathematically precise, which of course I do, the absolute value of r is less than 1. That means, by the way, that this series is going to add up to a number, and the geometric series is very friendly. It has a formula. We could figure out what number that adds up to, and you should be able to do that. But now let's take a look at this next one. This one all of a sudden has a new character in it. There's an x as well as an n. And when you get this new character, you have to make sure that your brain stays consistent with the fact that as n goes from 1, 2, 3, 4, 5, 6, 7, 8, it's that piece that keeps going from 1, 2, 3, 4, 5, 6, 7, 8. The x is it is not influenced by the changing n. Instead, x is going to represent a value, just like x represents a value in an equation. So we could make that x a 3, we could make that x a -8, we can make that x whatever we want. We don't even have to have a reason to do something like that. So if I just start daydreaming about replacing x with different numbers, I can come up with a conclusion about convergence or divergence. For example, if I replace the x with a 1, that is 1 over 4 to the n power. That's actually that series, and I know that's convergent. If I replace the x with a 3, then I really have the geometric series of 3/4 to the n power. Well, of course, that's convergent. But if I replace it with a 7, I have a 7 over 4. That's a divergent geometric series. So this is a pretty informal way of taking a look at an interval of convergence. Basically, if I go a 3, a 2, a 1, a 0, and even if I go into -1, -2, -3, those are all convergent. As soon as I go 4, 5, 6, 7, 8 in the negative direction, or 4, 5, 6, 7, 8 and onward in the positive direction, I have divergence. So if I think about it, there is an interval of x values that allow me to conclude convergence. And outside that interval of x values, I have divergence. So I can take this idea and put it into some math language. An interval of convergence goes from -4 to 4. Notice that I have soft endpoints, because if I plugged in a 4, that's a 4 over 4, which is a 1 to the n power, and that is actually divergent. So I can't include the -4 and the 4, but any x value in between there I can include. So I can think of it as a number line picture as well. Any x from that yellow shaded area is going to give me convergence. Any x from outside that shaded area will give me divergence. So this would be my interval of convergence, but I would also have a few other things, like the center of my convergence is x equals 0. That's dead smack in the center of my interval. And then the radius is how far I go out from the center to the edge. So my radius of convergence is a distance of 4. So I think at this stage you would agree that the concept of an interval of convergence is not all that taxing on the brain. It's just, hey, what x values make that thing converge? But remember, we used a very friendly geometric series here. The world isn't always going to be so friendly, so we can't maybe rely on this type of easy intuition. And in place of that, we're going to do some algebra. And even in this example, the algebra is going to be pretty easy. And I don't want to disappoint you, so I promise you that the algebra will get a little bit more exciting later on. But if I want to do the interval of convergence here, I say to myself, hey, this is a geometric series, and a geometric series is convergent when the inner guts, in this case it's called the common ratio, when the common ratio's absolute value is less than 1. All right, so if I want to turn this concept into an algebra equation, I have to say that. When is the absolute value of x over 4 less than 1? Now I'm willing to bet a lot of money that you don't remember the algebra technique for solving an absolute value inequality. Are you willing to take that bet? Well, it's pretty darn easy. To solve an absolute value inequality, you take the piece inside the absolute value and then you just say, hey, it's less than positive that and it's greater than negative that. And now you just solve this thing. In this case, I just multiply by 4 and boom, I have it. This is the exact same answer we got through some intuition before. So the idea of an interval of convergence, not really that overwhelming. It will get a little tedious with calculations later, but we'll build up to that.